So I know Newton's laws have taken me a while to explain, but it's because they're probably the fundamental most important idea of an intro physics class, because we're going to use forces to describe tons of stuff later on in the class. This is going to be the last of the instructional videos where I'm just talking about Newton's laws, and we're going to start doing some practice problems so you can actually see them in action a little more, and it'll probably feel a lot better since the ideas are still a little new to you once we get to the practice. But before we get to the problems, I've got to prepare you for something. There are some words in physics that can be very confusing because they're words that you've heard before, but you might not know exactly what they mean. I like to think of them as cuss words because remember when you were young and you heard a cuss word and you asked your parents, what does that mean? And they said, oh, I'll tell you when you're older, that's a bad word. In physics, there are some words that are just kind of bad until you've been doing physics long enough that you know what they mean. So instead, I'm going to give you some cleaner words that you can use. For the first one, we've got the word inertia. This word is used incorrectly all the time. Inertia is just talking about Newton's first law, and all it means is mass. Anytime you read the word inertia in a problem, I want you to just think mass, because that's all it's talking about, and the fact that, as you know, mass doesn't want to accelerate. You need a lot of force to accelerate a mass. So if someone asks you what has more inertia, a 50-mile-an-hour bullet or an elephant that's just standing there, you would go with the elephant because the elephant has more mass. Inertia has nothing to do with how fast you're going. Next up, we've got the word weight. I hate this word and I never use it in class. The only thing that the word weight means is force of gravity. That's it. A lot of people try to trip you up by getting you to confuse mass and weight. Don't fall for it. When you read the word weight in a physics problem, all they're talking about is the force of gravity. So if they ask you, on the moon, do you have less weight? Well, rephrase that. Say, on the moon, do you have less force of gravity on you? And the answer is yes. But if they ask you, do you have less mass on the moon? Well, no, you're still made of the same amount of stuff as you were on Earth. So don't confuse those two. When you see the word weight, it just means force of gravity. Another tricky one that comes up a lot is apparent weight. Apparent weight is talking about how heavy you feel, because how heavy you are and how heavy you feel are two different things. Your apparent weight is normal force, because how heavy you feel doesn't depend on how hard the earth is pulling you down. What makes you feel heavy is how hard the ground is pushing up on you. If you don't believe me, have someone jump on your back or go to the bottom of a roller coaster. How heavy you feel will change because of your normal force changing. And that's sort of like what we talked about in the elevator, right? If you're accelerating up, your normal force gets bigger, so you feel heavier. Your force of gravity isn't changing, it's your contact with the floor that's changing. Let me give you some more examples of Newton's third law before we hit the problems. So here we have a picture of a hammer that's striking a nail right as it happens. Now, according to Newton's third law, there's a pair of forces here that are equal to each other. And here's where that pair shows up. The force of the hammer hitting the nail is equal to the force of the nail hitting the hammer. Now, the difference is the hammer has a lot more mass than the nail does. In fact, you could get like a really, really big sledgehammer and you'd probably get a different effect, right? The forces are the same, but since there's a different amount of mass, then the amount that the object accelerates is different. In this case, the hammer has a lot of mass, so it doesn't accelerate quite as much, and the nail has a small amount of mass, so it has a huge acceleration and goes right on through. Or take sports as an example. Here's two football players where one of them is running into the other and tackling him. And there's two different things that are going to happen here. It's an interaction. The guy who's tackling is going to get slower, and the guy who's getting tackled is going to get faster. He's going to end up going this way. But the question is, well, why does one guy get more hurt than the other? Well, if you've played those kind of sports before, your shoulder still hurts when you tackle somebody, but your shoulder is a bit stronger than this guy's chest or wherever he's getting hit. Or what about the case of a baseball player hitting a ball? It's the same thing. During contact, the force that the bat puts on the ball is equal to the force that the ball puts on the bat. And it's the same thing that we talked about before. The bat has a big mass, so it gets a small acceleration, and the ball has a small mass, so it gets a big acceleration. But that doesn't change the fact that the velocity of the bat still gets changed a little bit in the swing. And for those of you who play baseball, you know what I'm talking about.